All right, so we got a lot to talk about today, and it is pivotal information for multivariable calculus. It's one of the very important concepts that we'll use for the rest of the semester. So we're going to talk about directional derivatives, and the gradient. The gradient is going to be our first really major result in multivariable calculus. All right, so we know that the partial derivatives, if we have z equals f of x, y, the partial of f with respect to x and the partial of f with respect to y tell us the rate of change in f in the x or y direction for some particular value of the other variable. So it tells us how rapidly the function's changing as we move parallel to the x-axis or as we move parallel to the y-axis. What we're interested in today is we want to find the rate of change of the function in the direction of any arbitrary unit vector. So what we're saying is if we're on some surface and we go in that direction, how rapidly does the z value change? How rapidly does our height change as we move each unit in that direction? So we're kind of picking a compass heading and saying, all right, we're going to go that way. How steep is the hill? How quickly are we going up? How quickly are we going down? We want to be able to do that in any direction. All right, so we're going to say that z equals f of x, y, and our unit vector is going to be AB, where the magnitude of u is 1. And we're interested in a particular point, x0, y0. So we're moving in the direction of this unit vector u on this surface z equals f of x, y. Let's draw a picture, and we'll start like we did in Calculus 1. We'll start by talking about an average rate of change. And then we kind of we'll slowly build up this idea to get our instantaneous rate of change. So here's our surface, z equals f of x, y. And we're at some particular point. There's f of x0, y0. And here's a curve that goes to some other point, f of xy. So if we project this down into the plane, in the plane, I'm going to call this P, this point, x0, y0. And we'll move along in this direction. And there's going to be point Q at xy. And the vector that we're talking about here is in the direction of PQ. So here's our unit vector. I'll make a thick line there. I'll do it in blue. So there's U. Oops. That, I wanted that blue. So there's my unit vector in the direction of the vector PQ. So the average rate of change as we move in that direction, we're just the difference in the function value, f of xy, minus f of x0, y0, over the magnitude of PQ. So just a difference in the function value divided by the distance that we move in the direction of PQ. So that gives us our average rate of change. Or interested in the instantaneous rate of change, so we need to take the limit as PQ, the magnitude of PQ approaches 0. So that's what we're going to do to get our instantaneous rate of change. All right, we're good with the idea here, our setup. So what we're going to do is manipulate this quantity to get something that we can actually relatively easily calculate. Actually, very easily calculate. All right, so our instantaneous rate of change will be the limit as the magnitude of PQ approaches 0 of this quantity, f of xy minus f of x0, y0 over the magnitude of PQ. Now, this doesn't look like a particularly nice limit to have to evaluate. So that's why we're going to do some more work with this. So we're going to call this quantity is called the directional derivative. Of f at x0, y0 in the direction of u. And we write, just in terms of notation, d sub u of f of x0, y0. So this is the directional derivative, capital D, directional derivative of our function at a particular point in the direction of this unit vector. All right, so our question now is, we don't want to have to deal with this limit. How do we calculate? So what we're going to do, let me set this up a little bit, similar to what we did with arc length and curvature, we're going to parameterize PQ in terms of its arc length. So we're going to use the argument, we're going to parameterize this vector in terms of its arc length. Well, it's a vector, we're moving in a straight line, so that parameterization is pretty easy. But that's the key to this argument, is parameterizing our vector in terms of its arc length. All right, so we're good so far. All right, so PQ is parallel to U. So we can write PQ as a scalar multiple. H times U for some scalar. H. So we can say if U is our vector AB, then PQ is HA, comma, HB. And our points here in the plane, let me go back here. Whoops, that's not what I meant to do. I meant to go back here. This point xy is going to be x0 plus some scalar multiple times a plus y0 plus some scalar multiple times b. That's going to get us from x0, y0 to xy, moving along in the direction of PQ. And y equals y0 plus hb. So this parametric equations for the line in the direction of u when we're in the plane. And the distance we travel along PQ is h. That's our arc length. That scalar multiple tells us how far we've moved in that direction. So we can say the limit as the magnitude of PQ approaches 0 of this quantity, f of x, y minus f of x0, y0, over the magnitude of PQ, is the limit as h approaches 0 of f of x0 plus ha, y0 plus hb, minus f of xy, or sorry, x0, y0, over h. So now this limit looks much more like our limit that we defined as the derivative. We had x plus delta x, y plus delta y, and we didn't have both happening at the same time. X plus delta x, y, or y plus delta y, x. That was our definition of our derivative in the x direction or in the y direction. So this looks more like a derivative. This quantity is going to be our definition of the directional derivative. And this is our directional derivative in the direction of our unit vector u at the point x0, y0. We're going to take this as our definition. Now, if u equals I hat or j hat, so we're moving, our unit vector is in the x direction or the y direction, the definition this becomes our definition of partial derivatives. So the partial derivatives are a special case of the directional derivative. Partial derivatives we can think of as a directional derivative in the direction of a I hat vector or in the direction of the j hat vector. Well, we have a nicer definition of the directional derivative, something that looks more like what we think of as a derivative, but we still need a way to calculate this. So we parameterized our unit vector in terms of the arc length. Our arc length is h, so there's our parameterization in terms of our arc length. Nice definition. We still want to be able to calculate. Well, what we're interested in is the partial derivative of f with respect to h. How fast is our function changing as we move in the direction of h, as we move along that little piece of arc length. Not the direction of h, as we move h units in the direction of u, our unit vector. So the partial derivative of f with respect to u as we move in the direction of our unit vector. Well, we can apply the chain rule here. So we can look at the partial of f with respect to h. All right, so we're good so far. By the chain rule, we can say the derivative of f with respect to h, how fast is the function changing for every unit h, is the partial of f with respect to x times dx dh plus the partial of f with respect to y times dy dh. And we usually shorthand this by writing f sub x at a particular point, xy. What's the partial, this should be an h. What's the partial of x with respect to h? Let's go back. We take the partial of this with respect to h. A, partial of y with respect to b, or h, b. So this is just going to be a plus f sub y at xy times b. And we can say at x equals x0, we're saying that h is approaching 0. So at that particular point, h is approaching 0. This is the same as saying the limit as h approaches 0, which gives us our instantaneous rate of change. Our derivative of f with respect to h, which is the definition of our directional derivative in the direction of u of f at x0, y0. Equals the partial of x, partial of f with respect to x at x0, y0 times a plus the partial of y at x0, y0 times b. This is how we will calculate the directional derivative. So we're going to take the partial derivative of our function with respect to x, partial function of the f with respect to y, multiply the x derivative with respect to x times the x component of our unit vector, multiply the partial with respect to y times the y component of our unit vector. Nice, easy calculation compared to those limits that we were looking at.
Can you go back one page on this script?
Mm-hmm. And if our unit vector is either I hat or j hat, this reduces to our partial derivative with respect to x or our partial derivative with respect to y at a particular point. All right, we good so far? All right, so directional derivative, that's a big idea. But this is going to lead us to leading us to an even bigger idea. So directional derivative gives us the rate of change of a function in the direction of an arbitrary unit vector. So we'll do some calculations in a second, but I want to add a couple layers to this idea. So this is our big idea for the directional derivative. And it comes from finding that instantaneous rate of change. All right. If our unit vector, just a quick note, if our unit vector makes an angle theta with the positive x-axis, and remember our unit vector, u is in the xy plane, it's in the plane, then our directional derivative of f we can write as f sub x cosine theta plus f sub y sine theta. So our unit vector, if our unit vector makes an angle theta with the x-axis, we can write the unit vector as cosine theta I hat sine theta j hat. So sometimes your unit vector will be defined in terms of the angle it makes with the positive x-axis. Another note, at a particular point, there are an infinite number of directional derivatives. We can choose to go in any direction, any compass head. So directional derivative, we can find an infinite number at a particular point. Just we can pick a different direction to go. All right, so before we calculate, I want to talk about our second major result, probably the more important result. What does this thing look like, sort of? We have something that just involves x times an x component plus something that just involves y times a y component. We're adding those together. It looks like a dot product. This is some x component, y component, y component. So the directional derivative looks like a dot product. And we can say that we can write it in this notation, f of xy equals this vector df dx, comma df dy, dot ab. Well, because this vector made of the partial derivatives of our function in the x component, the y component, we can continue with the z component, w component, however many we want. It comes up very frequently. We give it a special name. So I'm going to say this comes up often. In a number of different contexts. So we give it a special name. So we're going to say this is probably the most important idea from this section, is for z equals f of xy, and we have to have nice function with nice derivatives. We define the gradient vector. And our notation is del f of xy. So here's our second new symbol. This is a del. Or the symbol is called nabla. We say del, the symbol is nabla. We define that as the partial of f with respect to x, I hat, plus the partial of f with respect to y, j hat. And we could say for a three-dimensional vector, del of f of x, y, z. I'll write it in bracket notation, df dx, df dy, and df dz. So del gradient. We take the gradient of a function. We get this gradient vector. This del thing we call an operator. So this is really the first time we've formally talked about operators. And it has no value by itself. It has to act on a function. So it must operate on, I'll say, a vector or a function to have meaning. So by itself, we say del is defined as, three bars means defined as, the partial with respect to x, I hat, plus the partial with respect to y, j hat, and I'm just going to write it in 3 dimensions, plus the partial with respect to z, k hat. So it's not doing anything to a function right now. These are just partials, not acting on anything. We have to act, it has to act on some other thing for it to have any meaning. So for now, we're just going to let it operate on a function to give us this gradient vector. In chapter 15, we'll take the dot product and the cross product of this vector with what we call a vector field, and that will give us other stuff. So the del operator is going to be important, and our gradient vector is going to be extremely important. All right, so with this notation, we can write the directional derivative very compactly. All right, so everybody good with our gradient vector, our del operator. All right, so we can write that the directional derivative of f of xy is del f of xy dot u. And this is how I always think of the directional derivative. Del f dot u. That's the directional derivative. Del f is those partial derivatives with respect to x, y, and z, or x and y in this case, since we just have a 2-variable function. Take the dot product with our unit vector, and we have our directional derivative. And we're saying, just to re-emphasize, we're taking the dot product with a unit vector. Okay. So the directional derivative, important. Chapter 13, rate of change of a function in the direction of a unit vector. The gradient vector, extremely important from here through the end of the semester. The del operator, extremely important for, you'll see the del operator used in a bunch of different ways with stuff that you do in the future. Not just in Calc 3. Differential equations, electromagnetism, fluid dynamics, the del operator shows up everywhere. All right. One quick note. The gradient, del f, gives us a vector in the xy plane. It's not a vector in space. So del f is essentially kind of like a compass direction. It's a vector in the xy plane.
And you can't put it in 3 dimensions.
Well, we will work with it in 3 dimensions, but if we have a 2-variable function, the vector that we end up with is in the plane, not in
If we had a
space.
3-variable function, it would be.
It would be a vector in space. And we will use those del the del of xyz in certain circumstances to be a very, it turns out to be a very special vector. All right, so let's look at a calculation with the directional derivative and using the gradient vector. G of xy is the square root of x squared plus y squared. And my unit vector, well, a vector v. Well, in order to calculate a directional derivative, you have to know the direction that you're going. And our point is 3, 4. We want the directional derivative of g at the point in the direction of v. First off, what is this surface? If we think of this as a surface, g of xy equals x squared plus y squared. So z equals x squared of x squared plus y squared. That's a cone. And because we have the square root, that's just the upper cone. So this is an upper cone, circular cone. So our surface looks like this. Piece of our surface. So there's a cone. 3 I hat minus 4 j hat. So our unit vector is going off in this direction like this, or our vector is going off in that direction. So we're on the surface at point 3, 4. So here is 3, 4. So we're at this point-ish. So there's our point. And we're walking along the surface in this direction. We want to know what is the rate of change of our z value of our height as we walk in that direction. Well, we need a unit vector. So the magnitude of v is the square root of 3 squared plus 4 squared. What is that magnitude? 5. Magnitude of v is 5. So our unit vector, we need a unit vector for our directional derivative. Is 3/5 I hat minus 4/5 j hat. So we need to make sure we use a unit vector, del g. Partial with respect to x. What do we get? X over the square root of x squared plus y squared. And we get I hat. Plus, this is symmetrical, so we get the same thing just with a different y over the square root of x squared plus y squared. Now, and this is a j hat. I just want to kind of think forward a little bit. We're going to be doing a lot of stuff with this. What would be a really nice coordinate system to use here? Polar or cylindrical in 3 dimensions, because this is just r. So keep that in the back of your head. This derivative shows up a lot because these surfaces show up a lot. And so our directional derivative of g is 3/5 times x over the square root of x squared plus y squared plus, minus 4/5. We do the dot product. No, we made this in the direction, the unit vector in the direction of v. So this notation, you always use your unit vector. 4/5 minus 4/5 y over the square root of x squared plus y squared. And at our point, 3, 4, del g dot u is I plug in 3/4 and I get 3/5 times 3/5 minus 4/5 times 4/5 negative 7/25. So visually, we'd expect the directional derivative to be negative, right? If we move in that direction on that surface, we're walking downhill. So what this tells us is that at 3/4, g is changing. Negative 7/25 units. For each unit we move in the direction of v. So for every unit, if we're in feet, if we're in meters, whatever, we're going 7/25 feet or meters downhill for every foot or meter that we travel in the direction of this vector. If our directional derivative is positive, we'd be going uphill. This is a v. All right, yes.
Question regarding notation.
Mhm.
Is u vector always the unit vector, or do we use that, or is that now like always the unit vector, or do we
Well,
use
in
it
this
as a-
in this notation, the d sub u, that should be your unit vector.
So we can always name our unit vector
U,
vector.
yeah.
Okay.
But if you're not given a unit vector, you need to get a unit vector.
What do you just name a unit
Yeah.
vector? And if we're
Otherwise,
given-
otherwise the magnitude of the vector gets mixed up in your derivative. All right. Questions? So the directional derivative, important idea. The gradient, very important idea. Some properties of the gradient. Some of these properties are what make the gradient important. We'll talk about some more properties on block day. So we're going to use the gradient in a lot of different ways.
This is the last thing that
No, there's more after this. I told you it was long. All right, so we're saying we have z equals f of xy. And we're saying our function is differentiable in the area that we're interested in. So it's a nice function. The first property, if the gradient of our function is 0, and notice the gradient is a vector, then the directional derivative of f equals 0 for all unit vectors. So if we're at a point where the gradient is 0, that means that the directional derivative in any direction is 0. Well, what do you suppose is happening there? Flat. So what do you suppose is happening there? It's going to be the directional derivative being 0 in all directions is going to give us an extreme value. Where we're flat surface, we're going to be at the top of a hill or a bottom of a hill. That's going to be an extrema.
Are we going to have a method for finding extrema using that?
Yes, we will. The direction of the maximum increase in f is given by the gradient. The maximum value of our directional derivative is the magnitude of the gradient. So what this is saying is the gradient points in the direction of the steepest incline up the hill. So the gradient points in the direction of the steepest uphill direction. And we'll turn the gradient around. The direction of minimum increase is the same as maximum decrease. Is given by negative del F. The magnitude so the minimum value of the directional derivative is negative magnitude del F.
We put the negative into the vector part first or after?
No, it's the negative of the magnitude. Because if you put the negative in the vector, then you don't get the negative out of the magnitude. All right, 2 and 3 are easy to see. The directional derivative of f of xy in the direction of u is del f dot u. And that equals, we know that that equals the magnitude of del f times the magnitude of u times the cosine of the angle between them. What's the magnitude of u? 1. So that we don't have to worry about that in our calculation. What's the maximum value of cosine theta? 1. When theta equals 0. So that means the directional derivative and our unit vector point in the same direction. So the maximum value is when our unit vector is in the direction of the gradient vector. So that's when we get our maximum value of our directional derivative, is when we're moving in the direction of del f. And the minimum value of cosine theta? -1. When theta equals pi. We're moving in the opposite direction. Of del f. So our gradient vector gives us the direction to go up the hill the steepest, or if we turn around 180 degrees, the direction to go down the hill at the steepest at a particular point. Another important, that's a very important property of the gradient. Gives us the direction of maximum increase or maximum decrease. What would be the direction of no increase or decrease? So when the gradient and our unit vector make a 90-degree angle, orthogonal. So orthogonal to the gradient, a vector orthogonal to the gradient is going to give us a vector where we have no increase. So that means we're walking around a level curve of our surface at that point. So we're going steepest downhill this way, we turn 90 degrees, we're going level. So orthogonal to the gradient gives us no increase. Another important property of the gradient. All right, I have a question example, and then we will look at one more example. So we won't have to do any calculations for this one. What if we are given z equals, or f of xyz equals x e to the yz? We want the maximum directional derivative at point 2, 0, negative 4. So what is this asking us to do? The problem says f of xyz is x e to the yz. Find the maximum directional derivative at 2, 0, negative 4. What's another way that we could ask this question more directly? Find del f, the magnitude of del f at 2, 0, negative 4. That's, in other words, that's what this problem is asking us to do. Find the magnitude of del f at 2, 0, negative 4. That's going to be our maximum directional derivative at that point. All right, last example. F of xy, 9 minus x squared minus y squared. We want to find du of f at 1, 2, where u is cosine pi over 3 I hat plus sine pi over 3 j hat. Is it a unit vector? Sine squared plus cosine squared is 1. All right, what is the surface? Z equals 9 minus x squared minus y squared? What is the surface? So in the xy plane, z equals 9 minus x squared. Parabola, but facing down, and this 9 does what? Shifts it up. So it's an upside down parabola. So this looks like this. We get a paraboloid like this. That's the sketch in the first octant. No, this is just a sketch in the first octant.
Would it be closed on the bottom?
No, wouldn't be close. There's just a sketch in the first octant. And at 1, 2, what is z at 1, 2? 4? Is it 4? So we're at the point here. That's point 1, 2, 4. So there we are on that surface. Cosine pi over 3 I hat plus sine pi over 3 j hat. So which direction are we going? Are we going kind of this way? So there's u. What do we expect our directional derivative to be? The sign, at least. Negative. We expect to be negative. We're going downhill. Pretty steep downhill, right? Del f is minus 2x I hat minus 2y j hat. And del f dot u is minus 2x cosine pi over 3 minus 2y sine pi over 3. And at 1, 2, del f dot u is negative what does this come out to? Cosine of pi over 3? 1/2. There we go. Negative 1 minus 2 sine pi over 3. Square root of 3. Over 2. But we cancel the 2. But the y is 2. So we get 4, right?
Yeah, one of the twos has
One of the twos cancels out. All right. Negative. Just like we expected. What is the direction? So, what is the direction of no increase? So, maximum increase. Direction of maximum increase is del f at 1, 2, which is minus 2 I hat minus 4 j hat. So we're going steepest uphill if we're going that direction. What is the direction of no increase? So if we're going along a level curve here, how would we find that?
Find the perpendicular to the maximum.
How would we find a vector orthogonal to that one? What do we say? Someone said we could do 4 I hat minus 2 j hat. Switch the x and y, change the sign on one of them. What would be another one? Negative 4 I hat plus 2 j hat. So we could go this direction or that direction, and our steepest uphill is that direction. And this would be along a level curve at that point. What is a level curve at that point? What shape is a level curve? A circle. Okay. Homework. We figured out a circle. That's good. We're going to talk about some more properties of the gradient on block day. And then we'll do, not on block day, next time. We have a quiz on block day. The gradient is not on the quiz.
It's going to be a while.